So that was all well and good, and the general slicing method is fine, but we can make a cleaner method if it's a rotational object. So the disk method is the first method we're going to use for rotational objects. So I just mentioned that. In other words, there's an axis of rotation. So for example, you imagine this curve right here, and you imagine swinging it around and it will form a solid. I can actually show it to you in a graphic form. So if we revolve the item around the axis, you take that region and you rotate it around, it will create a solid, right, as it rotates around. Sorry, I forgot to click show solid. So as it rotates, it will form a solid. There, you can see a little bit better. So as it swings through, it forms a solid. So as you take that region and you rotate it around, in this case, the x-axis, it's forming a vase or a bowl or something like that, right? So a rotational object, and that rotational object has no hole in it. The disk method is particularly useful when there's no gap or hole in it, if it's solid. And you can see it forms that object as it rotates around. And we want to make a note that when we do this, it's a solid object. So let's make a note. The disk method is useful when there's no hole, right? When useful when the rotational object is solid. Right? It has no hole in the middle, right? So you're spinning it around. Now, it might seem strange, but that actually works for something like a vase because the volume is all the air inside. That's what we want to know. So you can imagine if the x-axis is kind of coming out this way lengthwise, you have a curve right there and you're spinning the curve around. Oh, and you can see me in the gold. Hi. In a weird shape, right? So you're spinning it around and it's forming this solid, right? In this case, a solid of air, but you're still getting to know that volume. So the disk method would be, it'd be you slicing across this with disks. All right, so now if I slice across that region, I'd be slicing across this region, and then when I rotate it around, it forms a disc, right? So I would take a piece of this like that. Take that piece, now rotate that piece around, and what it does, I'll take it right here. What it does is it forms a disc inside. So you take that and you rotate it around, it's going to form a disc inside. That's why it's called the disc method. Right? So you take that piece and you spin it around and it forms this thin disc, and then you know what you're going to do, right? You're going to stack up the thin discs inside, right? Stack them and stack them and stack them. But you take this zone right here, spin it around, and you'll have formed this disc. And that disc you can use to find the volume of the object, because if you can just stack up enough discs, you'd have it. It's sort of like a weird stack of coins, right? Where you start out with big coins and you get smaller and smaller and smaller coins as you go. Or, if you will, slicing up slides of potato. You thought you'd never see the potato again. It's the same idea, right? It's just that the discs are circles, right? As opposed to ovals, which is what they are in this case. But if you can stack them up, then you'll have the volume of the object. All right, so let's look at the drawing of this. All right, so for the disc method, you want to imagine like a stack of coins, or my potato, right? But the coins is better because my potato is not circular. So you want to imagine a stack of coins, right? So a stack of coins, which are discs, right? Or a stack of discs, right? That'll work. But they have no holes in them. That's why coins is great, because coins are circular discs with no holes. So the volume of the rotational solid composed of circular discs, because you're stacking up circular discs like coins, can be computed with the disk method, right? So if you have no hole, this is what you can do. So you imagine graphing the given function over the domain and range, right? You find and label your axis of rotation. Your axis of rotation must be labeled. We notate it with either a spinning arrow this way or a spinning arrow this way. This is if it's rotating around, say, the x-axis, and this is if it's rotating around, say, the y-axis. Right? Your spinning axis of rotation, which on a lathe would be the post that you're spinning around, that kind of thing. All right, we're going to draw an approximating rectangle. You always must draw this. And for the disk method, the rectangle that you draw is always perpendicular to the axis of rotation. Perpendicular. I'm spelling the word perpendicular wrong. Right? Because you imagine that, just do it right here. Your axis of rotation is right here. So you can see the axis of rotation. To show it's rotating, you put that little arrow. You're spinning around that axis. And when you do that, that little rectangle there forms this disc because you're spinning this way. So it forms that disc. So you have to draw that rectangle perpendicular to that axis of rotation. Okay. So it's always perpendicular. You label the thickness of your disc, always, right? And then you label your radius of rotation, which is going to be the hardest part, which is, in other words, you're doing the width and the height of your rectangle. Okay, so let me show them down here. So if I have a horizontal axis of rotation, like this, I would show it that way, right? I'm showing that it's spinning around this way. So this object is spinning around. Right? So you kind of have to visualize this in 3 dimensions at the same time that you're drawing it in 2 dimensions. You have a thickness right here, which is dx, because this is obviously on the x-axis for the thickness, aka the width, if you want to think of it that way. And if you're thinking, that sounds familiar, yes, that's why I had you using that language back for area of regions between curves in 6.2. Now the length of it is the radius of rotation. So it's the height or the length, whichever way you want to think of it. So it's right here. We also think of it as length. So length and height, we kind of use them interchangeably. So that height is equal to the radius of rotation. It's r of x. It's going to be some function of x. It's your radius of rotation. Why is it your radius? Well, because when you spin it around and form the disc, this is the radius of that disc. Now over here, same idea, right? Oh, here's your radius of rotation, right? Now, why does it work this way? Why is it, I'll deal with the right side in a second. So pi radius squared, pi r squared. Isn't that the area of a circle? Oh, yes. That's exactly what you're doing, right? Because you're taking this circle, right? That's circle and you're stacking it. So if you think of this disc that you formed, let me draw the disc. Right? So that disc has a thickness that's dx, and it has a radius, which is the distance from the x-axis up to that y value. That right there, from here to here, is r of x. And it's the radius of this disc. Sorry, it's supposed to be a circle. It's not, but it looks more like my potato. So it's a radius of that thickness, of that disc. And then you swing it around. What's the area? So area of a circle is pi r squared, right? So the area of this, the volume of the disc is pi r of x squared times the thickness, which is dx. All right? So what you're doing is stacking up the volumes of these disks. Sorry, change my color there. So you're stacking the volumes of these little disks and you're stacking them, and you're going to let dx be infinitesimally thin because of course you're going to let there be infinitely many disks that you're putting in here. Like a sushi chef really slicing fine into this object. And so that's what this is saying here. So you're doing pi r squared dx, right? You're taking the volume of a disk and then you're stacking them from A to B, from the start to the end. And then it works the same way with y as with everything else. I mean, it's all the same stuff. So except with y, this would be dy is my thickness. The length, or the height, whichever way you want to think about it. Just think about where I'm going to put this. Length slash height, whichever way you want to ponder it, is r of y, which is the radius of your disk, because you're rotating this way, right? Going around the y-axis. It's called the radius of rotation. And then your axis of rotation is that dotted line. You're rotating around the y-axis, so you denote that with an arrow up like that. All right. Now, what you're doing is you're finding, it's not really the areas, it's kind of the volumes, but it's area and then multiplied by an infinitesimal thin. So area is the pi r squared part, and then you multiply it by the thickness to get the volume, but you're doing it for infinitely many thin disks, like coins. And then when you stack them, right, when you add them up, which is where the dx and the a to the b form come in, then you're finding the particular volume of your solid.